Okay, we're going to wrap up Chapter 8 with proportionality theorems. This one basically is it's going to use a lot of the properties we've already been doing of proportional similar triangles, but it's going to add one more. So whenever we look at triangle proportionality theorem, it tells us that if we have a triangle and we have the lines, we have a triangle that's kind of made inside of another triangle. So here we have like the smaller one inside of this larger triangle, right? Just by drawing that extra segment. If the extra segment that's drawn is parallel with the base of that triangle, with the other side of the triangle, then it's going to divide the sides proportionally. So if you look at the statement down here at the bottom, it's showing that we have RT is proportional with the other section, QT, and RU is proportional with the other section, US. Instead of us having to do like the smaller side versus the long side, we can just do that one proportion. And then just like a lot of the theorems we've seen, this one also has a converse where we can do the opposite basically, where we're going to flip it, and it's still true. So if we know the reverse, we know that they are proportional with each other, then we can automatically know that those two sides have to be parallel. Okay, it's just the same theorem in reverse. So we look at this first example. It tells us that we have QS is parallel with UT, so that gives us already that triangle proportionality theorem setup. And so that means that we can compare the parts that it separates them into. So if I were to write my parts out, I'm going to do QR here would be proportional with QU, the other section. And so this would be equal to the other set of ratios on the other side, RS in comparison to ST. The top portion compared to the bottom, the top portion compared to the bottom. So if I plug my values in for these, I'm just going to substitute. So instead of QR, I'm still looking for QR or RQ. So instead, so if we could do RQ and QS is the same thing. So I'm going to term this as X. I always like to have a variable. If you want to leave it just as RQ, you're more than welcome to. So X is what I'm looking for here. So I'm going to plug in an X for my QR. My QU is 9. My RS is 4. And my ST is 6. Now that I have these proportions set up, I can cross multiply and solve. So if I do X times 6, that gives me 6X. 9 times 4 gives me 36. And so now I'm just going to divide to get X by itself. So I get that X is 6. So X was my RQ. So that means I have RQ is equal to 6. Okay, my proportions were able to let me solve for that. In the second problem, it has these triangles set up, and it gives us the lengths of all of them, and it tells us to explain why the shelf is not parallel. Okay, so in order for it to be parallel using our theorems, or our converse theorem, if you go back, our converse of triangle proportionality theorem tells us that if we can set up their proportions and they're true, then we can say that they are parallel. So we're going to set up these proportions. So if I look at my triangle, I'm going to do the top part. So I have my BC on the top here in comparison to the bottom of BA. And in order for them to be parallel, I would need them to be equal to the other side as well. So the top CD over DE. So I'm going to plug these in. So BC or CB is the same thing as 27. BA is 33, CD 44, and DE 25. Okay, so I'm setting these up. I'm still testing them. If you want to go back, you can put, we're testing these. I'm going to put like a little question mark above it. We don't know yet if it's equal. And so all I'm going to do is I'm going to cross multiply just like I did last time. So I'm going to do 27 times 25 on one side. I'm going to cross multiply the other way, so I get 44 times 33. So for 27 times 25, I get 675. And for 44 times 33, I get 1,452. So again, we're still testing if these are equal or not. So when we look at this, is 675 equal to 1,452? No, these are not true. So since they are not proportional, Okay, if we go back to like our statement right here, I can take off this question mark and I'm just going to cross through it that it's not proportional. Then that means that they are not parallel. So I can say that BD, that segment, is not parallel. You could maybe just cross it out, or let's just say it in words. We'll say then BD is not parallel, and I'll put not parallel symbol there, to AE. Okay, keyword that it's not. Okay, because they are not proportional. The next theorem that we're looking at is three parallel lines theorem. This theorem goes back to when we talked about transversals before. Remember that our transversals are lines, they're going to cut across two or more lines. And in this case, we have three parallel lines that these transversals are going to cut across. And this theorem just tells me, since the lines are parallel with each other, it's going to cut them into proportional sections. So if we compare the section between R and S, we can do one line compared to the other line. So here they had UW compared, so they could have done to VX. They did it in the opposite way, or I could do, you could do top line to line, or like they did in this example, they went across here. So they did UW to WY, and then VX to XZ. They set up those proportions. Okay, this theorem just tells me it's going to cut them up into proportional sections. So in example 3, it tells us that we have angle 1, 2, and 3, and it says they're all congruent. Okay, well, if we look at this transversal cutting across these lines, okay, this transversal here that has the angles all on it, if they are all congruent, that means that those lines are going to have to be parallel. Okay, because these are our corresponding angles. They're in that same position every time. They're in this top left position. And since they're all equal, it's going to make all these lines parallel with each other. All these streets are going to be parallel. So now it says GF is 120, okay, which they have it marked. DE is 150. CD is 300. And we want to find the length of HF. Okay, this is what we're looking for. This is my X. So since they're cut of them up proportionally, I can set them as proportions. So I'm going to do it as I'm looking for X, my total. So if I look at the same street, I'm going to do the FG, the top portion of the street I'm looking for, over my total, which is FH, what we're looking, the actual section we're looking for, or HF, whichever way, would equal FG was that top part. Now I'm going to look at the other section on the other transversal, so I can do ED is the top part there, over the total for them as well, which would be EC. So if I plug my numbers in, I get 120 over X, what I'm looking for. ED is my 150. And then EC, I just need to add it up, so I would do 150 plus 300. So if I go to simplify these, I still have 120 over X equals 150 over 450. I'm going to cross multiply to solve, so I get 150X equal to 54,000. Sorry. I divide by my 150 on both sides. Okay, don't be nervous when you get really big numbers because you're multiplying really big numbers there. But then when you divide, it's going to give you a much smaller number. So when I divide by 150, I get that X is 360. And so that would mean that HF, the section I was looking for, is 360 yards. Yards was our label there. Then we have one more theorem of proportionality. When we have a triangle, if we have a ray that's going to bisect an angle, okay, so here we have ray CD is bisecting the angle ACB, then it's also going to it's not going to bisect, but it's also going to create proportional segments on the other side. Okay, so the side that it cuts through here, it's going to make those parts proportional to the sides of our triangle. So the part that we created AD is proportional to DB, which could be equal to CA over CB. The way I like to keep, if it's the same side together, so I would have done AD is proportional to AC, the side, which is equal to DB, the section that it cut, compared to that side of CB or BC. Okay, either one of these is the same. Notice it would still have us multiplying the same exact numbers. AD is multiplied with CB. DB is still multiplied with AC or CA. They're just switched in positions. So here I have this statement. It says in the diagram, QPR is congruent with RPS. So it says use the given side lengths to find the length of RS. Okay, so they already have the X there for us in RS, okay, in our diagram. So if I want to compare my sections, let's first think about what QR would be. If we think about segment addition, QR added up with the other part of it, RS, would equal the total of QS, correct? So if I wanted to have QR, I could subtract RS over, and so I would get QS minus RS. If I plug those in, QS is my 15, RS is my X that I'm looking for. So instead of QR, I'm going to write 15 minus X. That's what I would be able to solve for QR. I would need to do 15 minus whatever value I get for X. So now if I set my proportions up, just like I did in the last one, I'm going to do QR, the section that's created by the bisecting ray, over the side, on that same side, QP, would equal RS over that side of PS. So if we plug them in, QR is my 15 minus X, QP is 7, RS is my X, and PS is my 13. So I'm going to cross multiply. Anytime that you have an addition or subtraction when you cross multiply, you should put that section in parentheses. So I would have 13 times my parentheses 15 minus X equals 7X. To solve this, I need to distribute my 13 inside. So when I do 13 times 15, I get 195 minus 13X is equal to 7X. And then I'm just going to keep solving. So I need to get my X's together, so I'm going to add 13. So 195 is equal to 20X. Divide by 20. And so I get for that side length 9.75. So that my RS would equal 9.75.